Hi everyone, my name is Alessio, and I'm glad to present this work on how recognizing view overlaps across two cameras freely and simultaneously moving in an unknown environment. View overlap recognition is the task of identifying the same scene captured by a camera over time or by multiple moving cameras. Multiple cameras can be present and used in immersive gaming, augmented reality, collaborative navigation, or for faster and more complete scene reconstruction. In our work, we focus on decentralized approaches that enable direct interaction between cameras and avoid single point of failures, as in the case of a single camera, or in centralized approaches that collect all the information on a single process unit. We also assume that the environment has enough texture for these approaches to extract corner-like points and corresponding features of the local neighborhood to represent a view observing the scene while the camera is moving. Existing methods use a coarse-to-fine matching strategy that first identifies view overlaps with features associated to the whole image, or view features, and then with local features. In our work, we assume that 3D maps are not available or reconstructed, and we propose to decentralize an efficient approach that was originally devised for a single moving camera. We design a framework that enables direct interaction and recognize view overlaps across two handheld cameras by decoupling feature extraction and cross-camera view overlap recognition. For each incoming frame, a camera independently extracts local binary features that are then aggregated into a hierarchical structure over time. We enable each camera to share their binary features of the current view at a predefined sharing rate and after an initialization window. Because these features can always be reaggregated by the other camera, there is no need to share any view feature. We assume that the cameras exchange query views on a communication channel that is always available, ideal, and reliable. When receiving shared features, a camera searches and matches candidate view features within its local vocabulary tree up to the current frame. After grouping and ranking the candidates, the view with the highest score is selected for further validation. The validation consists of matching the local features via nearest neighbor search and verifying that the bipolar constraint is satisfied via a robust fitting model like RootSIFT. To avoid ambiguities, we discard matches with a Hamming distance higher than a threshold and those that have a distance ratio between the nearest and second nearest neighbors too close to 1. Finally, the camera replies with a status denoting if a view overlap is recognized and with a corresponding frame in the sequence of the other camera. We compare the proposed framework based on the bag of binary words with 5 alternative choices for local features, view features, and matching strategy. And we refer to each version of the framework based on the main alternative components. Both DNetVLAD and DDBit replace the matching of view features based on bag of binary words with the view features directly extracted with a convolutional neural network. However, both variants preserve the sharing of orb features for the efficient coarse-to-fine matching. RootSIFT and SuperPoint replace the orb features with their classical or learned features. And SuperGlue replace the nearest neighbor matching by performing context aggregation, matching, and filtering in a single end-to-end architecture. For these 3 variants, and for fair comparison, the matched views are those identified by DNetVLAD. We also compare the use of a more recent robust estimator, MagSAG++, against the use of the classical RootSIFT for the validation of the matched views. As dataset, we use sequence pairs from 4 scenarios, and we annotate the view overlaps. The first 2 scenarios on the top and middle rows were collected by us, with both handheld and chest-mounted cameras. The other 2 scenarios were selected from 2 publicly available datasets. One is Courtyard, shown on the bottom, and the other is Office, formed from 3 indoor sequences in the TUM RGBD SLAM dataset. We use these sequences because there are no publicly available datasets with recordings from multiple cameras or with annotation of the camera poses and view overlaps. To annotate views in correspondence across the sequences of pairs of cameras, we exploited the 3D map and camera poses estimated by abstraction from motion pipeline, COLMAP, or the depth data in the Office scenario. We then computed the angular distance between the camera optical axis, the Euclidean distance between camera positions, and the visual overlap, as the ratio between the area spanned by projected 3D point within the image boundaries and the image area. To automatically obtain correspondent views, we constrain the angular distance and we set a threshold for the minimum view overlap. From the distribution of the annotated angular distances, we can observe how the scenarios widely vary in their viewpoint differences due to the multiple camera motions. As performance measures, we computed precision, recall, and accuracy. In this plot, we analyzed the impact of matching both view and local features compared to matching only view features. The two-stage approach achieves a higher precision recall on average. This is because wrongly matched views are invalidated, and there is a higher recognition of views not in overlap. However, there is a large drop in recall due to many views not identified in overlap with query views. We compared the recognition performance across the different strategies of our decentralized framework. RootSIFT achieved the highest mean accuracy. DDBOW, despite the 4 percentage points difference, is a competitive option for cross-camera view overlap recognition with higher median precision on average. DDBOW can also benefit of the fast inference of the bag of binary words and binary features for applications that may require nearly real-time processing. Different camera motion can affect the recognition of the view overlap, as we can see from the large standard deviation of all variants. Compared to RANSAC, the robust estimator MAGSAC++ does not contribute to improve the median accuracy of the cross-camera view overlap recognition. Here are some visual results of the matched views and matched local feature for selected query views of the 3 best performing variants of our framework. RootSIFT and SuperGlue use NetVLAD as view features to identify candidate views, and the matched views shown here are the same for both variants. Both DDBW and RootSIFT can fail in matching valid local features when the viewpoints or the distance between the two views are large. On the contrary, when the viewpoint differences are not large, matched local features tend to be in flat or localized areas of outdoor scenarios. SuperGlue has a strong capability to match a higher number of local features across most of the images, but it can also fail under very large viewpoint differences. To conclude, we presented a decentralized framework to recognize overlapping views across freely moving cameras. The framework is modular and can be combined with various view and local features and does not require a 3D map or any prior information about the environment. For facilitating comparisons and reproducibility, we provide the scenario and corresponding annotation in our webpage. Finally, we will address the scalability of our framework to more than 2 cameras and the robustness in lossy communication channels as future work.